T-minus 10, 9, 8, 7, 6, 5, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis on a mission to build, resupply, and to do research on the International Space Station.
Houston now controlling. Atlantis begins its penultimate journey to...
Alright, picture this. You're standing miles away from a launch pad. The countdown hits 0. And then, boom, a fiery burst lights up the sky. A rocket soars straight into the air, punching through the clouds with what looks like a vertical fury. But here's the question. Why straight up? Why not at an angle? Or in a curve? Or even horizontally? It seems a little counterintuitive, doesn't it? We know Earth is round. We know that rockets don't go to space and just stop there. They orbit the planet, circling it at incredible speeds. So if the goal is to orbit, not just to go up, why do we begin by launching rockets vertically? Today, we're answering that question, and diving into the physics, efficiency, and strategy behind one of the most iconic visuals in modern science, the vertical rocket launch. The point isn't up, it's fast sideways. Let's start with a surprising truth. The goal of most rockets isn't just to get high, it's to get fast. Specifically, fast enough sideways to stay in orbit. To stay in low Earth orbit (LEO), you don't need to be that high, just about 200 to 400 kilometers up. But you do need to be moving at around 28,000 kilometers per hour, or about 17,500 miles per hour, sideways. So, the question changes. If rockets need to go sideways really fast, why don't they just launch sideways to begin with? The answer comes down to air, gravity, and fuel. Why we launch vertically, fighting gravity smartly. Gravity is relentless. At Earth's surface, it pulls everything down at about 9.8 meters per second squared. If you tried to launch a rocket horizontally, you'd have to fight two battles at once, gravity pulling you down, and air resistance slowing you down. That's incredibly inefficient. By launching straight up at first, a rocket escapes the densest part of the atmosphere as quickly as possible. Think of it this way. The lower you are, the thicker the air. The thicker the air, the more drag and heating the rocket faces. More drag equals more wasted fuel. So, going straight up punches through the thickest atmospheric layers fast, reducing resistance early on. Once you're high enough, and the air gets thinner, then you can start turning. The gravity turns straight up, then curved path. Here's where it gets cool. Most rockets don't actually go straight up the entire time. That's just how it looks at first. Shortly after liftoff, sometimes just 10 to 30 seconds in, the rocket begins a slow, deliberate curve called a gravity turn. It starts with a tiny tilt, called a pitch-over maneuver. Then gravity itself helps bend the trajectory gradually into a sideways arc. This maneuver is efficient because it minimizes fuel use, uses gravity to help guide the arc, reduces structural stress. By the time the rocket exits the atmosphere, it's already pointing more sideways than up, building horizontal velocity to reach orbit. So straight up is really just the first step, a tactical choice to beat the thickest air and strongest gravity, before transitioning into orbital motion. Air resistance, the invisible enemy. Let's go deeper into drag for a second. Air resistance might not sound like a big deal, but at thousands of kilometers per hour, it's a serious threat. There's a point during ascent called max Q, short for maximum dynamic pressure. It's the moment when the combination of speed and air density puts the greatest pressure on the rocket's structure. Too much stress at max Q? Boom. Catastrophic failure. That's why rockets throttle down just before max Q, then throttle back up once they're through. Launching straight up helps a rocket get past max Q faster, and spend less time in high drag conditions, saving fuel and protecting the hardware. So again, vertical at the start equals safer and smarter. Fuel efficiency, the tyranny of the rocket equation. Here's a hard truth about spaceflight. Fuel is heavy. Really heavy. The vast majority of a rocket's mass at launch is just fuel. Not astronauts. Not satellites. not gear. Fuel. This is because of the rocket equation, which basically says, to go faster you need more fuel. But more fuel means more mass. Which means you need even more fuel to carry that fuel. And on and on. So rocket engineers have to make every gram of fuel count. That's why vertical launch, followed by an efficient gravity turn, is ideal. It uses just enough energy to escape the thick atmosphere and then channels most of the fuel toward reaching orbital speed, not just height. Every second spent pushing against unnecessary drag or gravity costs precious fuel. Why launch sites matter? Now you might ask, if it's all about speed and efficiency, does where we launch from make a difference? Absolutely. Most launch sites are close to the equator. Why? Because Earth itself is spinning at about 1,670 kilometers per hour, 1,040 miles per hour, at the equator. And launching eastward from there gives your rocket a free boost. It's like hopping on a moving walkway at the airport. Earth's rotation gives you a head start toward orbital speed. That's why NASA launches most missions from Florida, and why the European Space Agency uses French Guiana. It's not just about weather, it's about orbital mechanics. Beyond orbit, what about Moon and Mars missions? Okay, so this explains how we get to orbit. But what about missions to the Moon, or Mars, or beyond? Interestingly, they launch the same way. First straight up. Then sideways into Earth orbit. Then, once in orbit, they fire their engines again to leave Earth's gravity well and begin the long journey outward. This two-step strategy, Earth orbit first, then escape, is far more efficient than trying to blast directly from the ground to deep space. In fact, no modern mission launches directly from Earth to the Moon in one go. It's just too inefficient and expensive. Why it looks so simple, but isn't. The vertical rocket launch has become such a familiar image that we often forget how precise it is. Behind that straight-up path is years of trajectory planning, minute-by-minute calculations of air pressure, wind, rotation, and timing, constant adjustments mid-flight by onboard computers. Even the tiniest deviation can result in a failed mission. And if you're wondering why rockets don't immediately flip sideways once they're high up, it's because timing is everything. Turn too soon? You fall back to Earth. Turn too late? You waste fuel and miss orbit. Turn at just the right time? You ride gravity like a wave. Final thoughts. So, why do rockets launch straight up? Because going vertical, at least at first, is the smartest way to beat gravity, minimize air resistance, and set the stage for orbit. It's not about going up forever. It's about going up just enough, and then turning just right, to go fast enough sideways that you never fall back down. It's physics. It's strategy. It's centuries of trial and error distilled into a perfect upward arc. And the next time you watch a rocket pierce the sky, remember, that vertical streak isn't just a symbol of power or progress. It's a monument to efficiency. To the art of bending natural laws just enough to escape them. And to the beautiful dance of thrust, gravity, and motion that sends a little piece of Earth out into space. If this launch into orbital strategy got your curiosity off the ground, don't forget to like, subscribe, and share it with the fellow space nerd in your life. And here's a question for the comments. If you could ride any rocket in history, Apollo, Falcon 9, Saturn V Starship, which one are you picking, and why? Until next time, keep looking up, and keep asking questions that go beyond the surface. Because as we've just seen, the path to space is anything but straight.